So far we have discussed, scalar field theory and harmonic field theory. And in the last lecture, we have seen that, okay, there is some kind of interaction between Fermion and scalar fields, right? And then how to calculate the scattering process, or in fact, the decay of the scalar field into pair of fermions. So today, we'll take a little bit of departure from the discussions of field theory, and we'll see that there are some additional source of symmetries could be there in our theory. So we'll talk about them, and from there we'll try to understand that whatever the symmetry we have discussed so far. Okay, so then the symmetries are guided by some kind of transformation parameter, right? And those parameters are basically space-time independent. So now, what is the situation of field theory when those parameters are space-time independent? That means they are global. The value of those parameters are independent of the space-time. Okay, and then how the field theory changes when those parameters become space-time dependent. That means local. Okay, so that's why today we'll have a discussion on symmetry, but this symmetry is more on the internal space. Okay. So what is the meaning of this internal space? So this is not certainly the space-time symmetry. So whenever there's a quantum field and we try to associate this quantum field theory description with the particle physics, then in the context of particle physics, we talk about particle creation, annihilation, their scattering, and all those things. So there must be some kind of guiding principle to compute them. To do so, we need to have a primary information about the Lagrangian. Because Lagrangian tells what is the dynamics of those particles, right? And how do they interact among themselves. Now, for the free field theory, we know if we restrict ourselves to, let's say, spin 0 and spin half, what we have discussed so far, right? Then what is their dynamics? That means what is the equation of motion? Dirac equation, Klein-Gordon equation, so on. But when we talk about, for example, how do they interact? That means, is there some kind of a conservation of some kind of symmetry, or the quantum numbers is required or not? How do they transform, and all those things? Those informations are needed. And that information can be extracted based on the internal symmetry space, how those quantum fields or the particles, they transform under them, right? So that is the idea. So here we talk about the quantum fields, which are the representative for the particles. And to understand the symmetry principle, we have to understand the okay. So when you talk about the symmetry, that more or less towards the representation theory. The representation theory that you understand. Okay. So most of the cases in the symmetry that we talk about, where the parameter changes continuously. So that's why we talk about the continuous symmetry. I'll give you a explicit example and all those things. But there are also possible cases when the things can be discrete. So we'll not go much about the discrete symmetries, because that we generally impose by hand. For example, Z2 kind of symmetry, as you know. So if I have a scalar field phi going to minus phi, if we impose the Lagrangian is invariant, then we say that, okay, Lagrangian is Z2 symmetric. That's why whenever you have an odd number of fields, these are basically Z2 non-conserving fields and so on. So whenever needed required, we'll talk about the discrete symmetries, but our primary focus is basically on the continuous symmetry. Now in the continuous symmetry, there are few symmetries that almost all of you are familiar with. For example, phase rotations when you talk about in two dimension. Okay, and if you take a modular one radius of rotations, then you talk about, let's say, any, if you think about in terms of quantum fields are being rotated, then you say, okay, psi is rotated by this value, it is for I theta psi, right? And this is just like a phase rotations, okay? And this theta is the parameter of the rotation. Theta is the parameter of rotation. Now, this theta can be global. That means whatever be the value of the space time, okay, theta doesn't change, theta picked a very fixed value, then you call it a global, or it can have a also the following from the theta is a function of x and t, okay, and then or in the relative covariant form we write down theta as a function of x, so basically x mu, right? So then we say, okay, theta has a space-time dependence. Now, what is the difference between them? So you can see that if theta has a space-time dependency, then whenever there's a derivative operator in my Lagrangian or any part, okay, so when they act on them, that will be non-zero contribution. Where in the case of where you have a theta is a global parameter, then the derivatives, any kind of derivatives, the acts on them will be zero. Okay, so that's how we'll see that what kind of new things can appear when theta becomes global to the space-time dependent, which also we called local. Okay. So now, what is this e to the power I theta? So if you think geometrically and you draw a uniradius circle, okay, and this angle is theta, so e to the power I theta generates all the points on this cycle because theta is taking a continuous value. That's why this is part of a continuous symmetry. When you make theta to be discrete, then these transformations will be not continuous, but like a kind of a hopping, like for example, the lattice points, you do hopping kind of thing. So that's a discrete symmetry. For example, if you choose theta equal to 0 and pi, that is nothing but your transformation under the Z2. So that's why you can understand this Zn, which I call Zn here, it is actually equivalent to e to the power I 2 pi by n. So where theta is changes by 2 pi by n. Okay, so that's why the Zn discrete symmetries are basically, you can think of, they are the subgroups of your this rotation symmetries. Now, what is e to the power I theta? So certainly this is a unitary, right? E to the power I theta is a unitary transformation, right? Because if you define as a u, so u dagger u equal to identity, right? So because theta is a real parameter, yeah, so I should also mention that that is a real parameter. Okay, so that's why this u dagger u equal to identity. So this is like a unity transformation, and from the quantum mechanics, even you know that if you have to keep the norm of the state to be conserved or the invariant, then that's basically you play with unitary transformations. Okay. Now that's the u, but what you can consider this quantity in the following format. You can think of e to the power I. There is some identity matrix and then the theta. And this identity matrix is basically 1 by 1. That means just an element. So that's why, and this is one dimension. That's why this is called U1 symmetry. So this 1 stands for, this is in the complex sense, 1 by 1 elements. And U1 have only one generator, and that generator is basically sitting here, which is proportional to your identity matrix. That's why U1 is abelian, because if you have only one generator, it commutes with itself. So U1 is also the abelian group. Okay, so U1 is the simplest abelian continuous group, and E1 doesn't have any kind of representations, what E1 only can have, it can have the charges. Now, what is the meaning of charges? That when this E1 operator, E1, if I define this as some kind of Q operator, now if I take any quantum state psi, okay, so this Q acting on that state is basically giving this eigenvalue Q, right? So that's why when this U transformation acts on the state, it's eventually I can write down to the power I Q theta, and that is the generic E1 transformation with a charge Q of a state. Now, depending on the nature of this Q, we have different kind of abelian symmetries. Okay, for example, if you have a lepton, EQ is the lepton number, then we call it E1 lepton number. If it's a baryon number, we call it a E1 baryon number. When there's a B minus L symmetry, we call it E1 B minus L, or sometimes we give some arbitrary X abelian symmetry. And the contested standard model, what we have Y1, E1 hypercharge symmetry. So the basic differences for this among these different E1, what is the assignment of these charges to this quantum field? Okay, the mathematics associated with them are basically exactly same, and that way state should transform under this abelian symmetry is basically follow the similar rule, which is e to the power I
Hello,
Q.
sir.
Yes.
Sir, I did not understand one thing that is you have written to the power IQ theta.
Hmm.
So I want to know that this charge, is it anyway related to the Noether charge that you have been discussing last class?
What charge?
Noether charge you taught in the last class, I think.
Not usually. Not usually. It is an internal symmetry space. Okay, that you can also calculate, but Noether's theorem is much more bigger than that. So it's better not to connect with that thing immediately. Okay.
Okay.
This is just a
And
quantum
also,
number. It's just a quantum number.
and e to the power IQ theta, what does this represent? Is it representing the state or the charge?
No. So if you remember the quantum mechanics, how to transform a state under rotation? It's basically a quantum state psi is transforming as e to the power I theta. That's the first thing that I written down. So you can think of the quantum mechanics, then you just write down this equation as psi transform as e to the power I theta psi, right? So now your states, which are the quantum fields, they are the operators. So this is the state associated with the particles. How do they transform? So the amount of transformation depend on what is the charge. Okay. For example, if you have a E1 lepton number, let's say, and now you take two different electronic field, psi L1 and psi L2, and their charges are, let's say, Q1 and then Q2. So the E1L symmetry is e to the power I Q theta, right? But when you transform this psi L1, so the psi L1 will transform as e to the power I E1 theta, psi L1, psi L2 will transform as e to the power I Q2 theta, psi L2. So though the transformation property are the same, but because their charges are different, so the amount of rotations are different for different fields. Okay?
Okay, sir. Okay, sir. Thank you.
Okay. Yeah. Any other question? Fine. So that's why we'll see when we talk about the standard model that there are quarks, there are leptons, there are Higgs fields, and so on, and they have different hypercharges. So that's why the amount of rotation due to this U1Y actually depend on what is the charge associated with that. So what is common? The way it is transforming. Okay. What is not common between them? How much it should transform. So the strength of the transformation determined by the charge as E1 charge associated with that particular field. Okay. But the way of transformation is basically unique as long as you keep your symmetry group same. E1. Okay. Okay.
Hello, sir.
Yes.
But in quantum mechanics, these states are same state, because these states are rays of states that can be different, can have different phases, state with different phases. So that states can be two different state or same state with some up to a phase. These state last
No.
two line.
No. In quantum mechanics, if there is some phases which are basically nothing associated with any kind of quantum number, they generally sometimes appear as overall phases. Okay. So that is not important in our case. But if you remember the spherical harmonics, okay, there are also e to the power I theta L kind of, or m e to the power I m theta. Now you see that if the m values are different, that e to the power I m theta rotations are different, right? So that's why depending on different kind of angular momentum states, their projections are different. The rotations in the space e to the power I m theta, that will be different.
Oh, okay. One thing, sir, these quantum numbers, the Q1 and Q2, is these are integer or any can be any value, means fraction can be also there.
That depends on the symmetry. For example, if you talk about the electromagnetic charges, for electron it is integer, but for the quarks it's a fraction, right?
Means in quantum mechanics we have seen if theta is periodic, then m is integer. In this case, if theta is related to 0 to pi, then q is integer. So if we restrict theta to be periodic, then q is integer.
Yeah, but the point is basically your periodicity also depends on what is your quantization depends on the periodicity, right? So who tells you
Yes.
your periodicity is always 0 to 2 pi? It can be 0 to 4 pi, 0 to 6 pi. Nobody guarantees that all the fields will have periodicity at 0 and 2 pi, isn't it? So quantum mechanics is not the fundamental thing here. The fundamental thing is the mathematics part. Okay. The part of is basically what we have done in the quantum mechanics. That's a different thing. That cannot be exactly what we are talking about here. And
So in case of quark,
talking about, that's basically quantizations. Okay, so quantizations is a different thing. You can energy quantize and all those things. Here, the internal symmetry is a compact. That's why they are quantized. So that's why Q's, the charges are basically quantized here.
so charges has quantized due to what?
Due to the symmetry, they are compact.
Okay, symmetries are compact. So for quark field, the charges are not integer multiple of electric charge. So for
What
that
do you mean by the
case,
integer multiple? They are 2/3, 1/3. So what do you mean by that?
yeah, yes.
No, they are not in.
I mean, there are
Fraction.
fraction of electric charge. Yes.
Yes.
So for that case, compact.
Yeah. Compact tells you the discrete. So it's a discrete, 2/3, 1/3. Compact doesn't tell you it will be integer. It depends on the boundary conditions.
Okay.
Yeah, that's the confusion you have. Yes.
Okay. Thank you, sir. Got
Okay.
it.
Hello, sir.
Yes.
Sir, as far as the discrete symmetries are concerned, when you are saying that we can put them by hand, so means like, can you elaborate? Means like how we are putting it by hand? Means like.
For example, by hand, basically, as I impose the phi going to minus phi. This is the I am imposing here, right? By the transformation properties. Okay. So discrete symmetries in the Lagrangian we'll put by hand because we don't easily gauge the discrete symmetries. So, and we make them very much global. Okay. So the kind of discussions we'll be talking about, we don't impose the symmetries the way we gauge the symmetry, the continuous symmetry, and so on. Okay. It's like a hopping kind of assignment. So I have a much more freedom for the discrete symmetries.
Okay, fine.
Okay. So why I'm calling them charges? Because this is just a quantum number. So charge is nothing to do with the electric charge. Any kind of quantum number in this language we call charges. That's why. Okay. Okay. So now, if we have this kind of global rotations, so now you see that this actually restrict the form of the Lagrangian. Let's see how. For example, let's say I have a complex scalar field psi, and this psi is transforming as e to the power I theta phi. Okay. So then how the phi dagger will transform? Phi dagger will transform into the minus I theta phi. Just the conjugate of this, and theta is a real parameter. Right. So then if I do Lagrangian, and if I demand that this transformation, which I'm calling a E1, okay. So this Lagrangian is invariant under E1. That means all the terms in the Lagrangian must be invariant under this E1. So if you write down a kinetic term, so this is the kinetic term, write down. This is the mass term, and then basically we write down the potential term. Okay. So now if you forget the potential term to start with and focus on the kinetic term and the mass term, what we'll see that if my phi is transforming as e to the power I theta phi, then del mu phi will transform as e to the power I theta del mu phi. Because your theta is a global parameter, theta does not have any space-time dependency, so that's why I can change this thing. And then my del mu phi dagger will transform as e to the minus I theta del mu phi dagger. So if I take del mu phi dagger, del mu phi, this will be del mu phi dagger, del mu phi. Now see that these two phases are actually opposite. So they will cancel and this kinetic term remains invariant. Similarly, m square is not transforming under the E1. So my phi dagger phi will goes as phi dagger phi. So this mass term also remain invariant. Okay. So then what will be the form of potential? I can write down such that it is E1 invariant. So then you can see that if phi dagger phi is invariant, then my V phi dagger phi must be of the form of Cn phi dagger phi to the power n equal to, let's say, 2 to any number, infinity. I can write down, right? But only thing, if I restrict myself to write down the potential terms such that these are the couplings or the, right? So these couplings should not have mass dimension more than, less than less than 0. So that's why I restrict myself to write down as a C2 phi dagger phi square. That's all. So if I have to write down E1 invariant Lagrangian with a complex scalar field, then I have only possibilities are this m square phi dagger phi minus C2 phi dagger phi whole square. Right? So now you can see what is the role of the symmetry. The symmetry is actually putting some kind of constraint. Symmetry is actually prohibiting to write down any random term in the Lagrangian. Okay. So that is one of the role of the symmetry. And so you can understand that when we try to construct any kind of new theory, what we do first, we try to understand the system, and based on our knowledge, we try to say, okay, this system may have these symmetries, fine, and then this system has these fields or the particles, and then we assign, okay, these are the representations, or this is how the field transform, right? And if we know how the fields are transforming, then we know we can write down this composition of these fields in such a way that they respect the symmetry. That means these terms are invariant under the symmetry, and only these invariant terms we can collect and define our Lagrangian. So if we have the information about the quantum fields and the symmetries and how the quantum fields transform under that symmetry, we can write down our Lagrangian uniquely. Uniquely in a sense, we can always write down the total derivative terms, but that will not certainly, affect our observables or what are the things that we are going to compute and measure. Okay? Yeah, up to this part, any question? Fine. So now, as I told that E1 doesn't have any kind of representations because the one-dimensional representation there. So what we can do, and remember, so E1 is a complex rotation, right? So the equivalent rotation you can think of in the following form also. So if you have defined your rotation matrix as R, so which is a two-dimensional rotation, theta. So this will actually mimic the very similar to what is E1 is doing, but this is the orthogonal rotations in two dimension. So this we call as a O2. Okay, O2, O stands for orthogonal and 2 stands for two-dimensional. Now you can understand there is a relation between this O2 and E1. They are actually homomorphic to each other. So in a real space, if we think about the rotation, you will think rotation in terms of O2. So now, if you try to reconstruct the very similar this Lagrangian, okay, in terms of this symmetry, how do you start with? You start with a complex scalar field, right? So now you know a complex number is basically nothing but a collection of two real numbers. So similarly, a complex field you can write down as a two real field, okay? And then your phi dagger would be written as a phi1 minus I phi2. So then you can construct an O2 two-dimensional representations, which you write down as a phi1 phi2, and this phi1 phi2 will be rotated as R acting on phi1 phi2, okay? And we know that R transpose R equal to identity. So you can construct a Lagrangian which is in the particular form. So okay, I'm not thinking about the normalizing this 1 by root 2 and all those things. If you want to do that, you can certainly normalize them, but that is not much of our discussion here. So what you can calculate now that okay, del mu phi1 plus del mu phi2 times del mu phi2 minus m square phi1 square plus phi2 square minus C2 phi1 square plus phi2 square whole square. So you'll see that this is the invariant Lagrangian which respects this O2 symmetry. And also you can say that if you start with this Lagrangian and replace the value of this phi and phi dagger by phi1 phi2, you generate this Lagrangian. So eventually, whether you are trying to understand the Lagrangian in terms of complex field or the real fields, okay? So that's why the E1 and O2 invariant Lagrangian will be actually very similar to each other. Only the basis in the basis where you are writing the Lagrangian, they are different. One Lagrangian you are writing in terms of the real scalar field. One Lagrangian you are writing in terms of the complex scalar field. Okay, and mathematically these are equivalent. E1 and O2, and there's a relations between the homomorphism is there. Okay, fine. So now this similar to E1. O2 has also only one transformation parameter, and now we'll talk about something called the generators. Now, what is this generators? by the name you can understand. So the generators are basically whose repeated action actually generates the whole symmetry space of the group space are called the generators. Now, if you recall the idea of the linear vector space, where you have the concept of basis and all those things, so these generators form a basis in the symmetry space. That means if you can identify a symmetry space, okay, and then you immediately identify for at least the kind of group we'll be talking about, the number of generators, and then you can say the symmetry space is that dimensional. For example, O2, how many real parameters are there? So there's many ways mathematically you can calculate the number of generators and so on, but we will not go into detail about that thing. So what we'll calculate is basically we talk about a orthogonal matrix, okay, which is assumed to be an n by n matrix, okay, and then we calculate that how many independent real parameter I require to construct a n by n orthogonal matrix. If I can count that, then I know that will be the number of generators, because generators are also independent, and that actually mimics the number of independent real parameter in that space. Okay. So if you calculate that, then you find out the number is n into n minus 1 by 2. Now you see, if you talk about the O2, okay, for O2, you have only one real parameter, which is reflected by the theta, and O2 has only one generator. So my O2 has a one generator. Okay. Or more specifically, you can say SO2, special orthogonal, because you just impose and then, okay, let me be more careful. So it's like a, here, you set the condition that determinant of O is 1. Instead of plus minus 1, you set the determinant to be plus 1. So when you impose this additional constant, then you give a special name to them and you call it S. S stands for special. Okay, so special orthogonal group. So that's why this O2 that we're talking about, even if you impose the determinant is basically 1, then they become a special orthogonal group in 2 dimension, and that has only one generator. So similarly here E1 also has one generator. Okay. But now if you have only one generator, by construction they are abelian. So both are abelian, but we should look for the what are the higher symmetries. Okay, the next higher symmetries is basically you can think of beyond E1 is basically U2. But as I told you that if we talk about our particle physics and the standard model, then you look for only those symmetries where the determinant is 1. So that's why instead of looking for U2, we look for special unitary group. So these are called special unitary. Special because you fixed the determinant of them to be 1. Okay. So now if I start with a very generic complex matrix in 2 dimension A, B, C, D, now each of these elements are basically complex. So you have a B1 plus I B2. In this way, you will have 8 such elements. And then you impose the criteria that if you define this matrix to be U, that U dagger U equal to identity, and determinant of U is 1, then you will find out you require basically 3 real parameters. Okay, so you require 3 real parameters, and that tells you the number of generators for SU2 is 3. Okay, so now if I talk about the SUN, where you have an n by n unitary matrix whose determinant is 1, then the number of generators you basically write down n square minus 1. And then you can see that SU2 n equal to 2, so you have a 3. Okay, So the group that will be interested in U1, SU2, and SU3, because these construct your standard model. Okay, so we'll discuss now the SU2 group in detail. So,
Hello, sir.
yes,
Sir, what do you mean by 3 real parameters?
3 real parameters means basically if you think about, let's say, Eulerian rotation, okay? So you have a 3 independent rotations, and these 3 independent rotations are θ1, θ2, θ3, right? So these are 3 independent real parameters, and that's why you only can have in the 3 dimension 3 independent rotations, and the number of real parameters are associated with 1-to-1 with the generators. That's why the number of generators are also basically the same. That's how you can count.
So I want to ask that
Hmm.
once we put, let's say, we have taken considered a very general form for the U, that is, you have written A, B, C, D.
Yes.
And once we put the condition U dagger U is identity and determinant U is 1, then it will put such restrictions on this term, and it will turn out to be only
Yes.
3 real parameters that will be existing in this U in the
Yes.
form of this okay.
Okay. So
And that follows for all higher orders also, not only for SU2. The same formalism is
no,
followed
that's why I
for
said that
SUN.
using this constant, so if you start with the SUN, okay, the SUN generic complex matrix n by n, you will have 2 n square number of elements, real elements, okay? Then you will, if you impose the unitarity condition, you will get n square such condition, and then it becomes 2n square minus n square, okay? And then you impose a conditional determinant, and determinant give you only one condition, so that is -1. So this becomes n square minus 1.
So, okay, sir.
Okay. Okay. Any other question? Okay. So now the group that are talking about the SU2 and SU3, so if they are basically part of your SUN group, and this group, they will have this n square minus 1 number of generators. Okay. And as I told you, these generators actually form a basis in that symmetry space. So that means if you think about SU2, it's a 3-dimensional space. Okay. And then each coordinates are basically not each basis vectors, unit vectors, if you think about, and then they are represented by one of the generators. And that's why whenever you write down any such matrix which has a similar property, okay, with a 2x2 complex matrix, determinant 1 unitary, and that you can write down the linear combination of these 2 generators. And that's what we do in the vector space, that if you know your phi I are basically your basis vectors, then any arbitrary vector psi you can write down as a sum over Ci phi I, the linear combination. The same thing you can write down any arbitrary 2x2 unitary with determinant 1 matrix, you can write down as a linear combination of these 3 generators. Okay, from that sense, they form the basis in that vector space, which is the symmetry space. Yep. Now, interestingly, these generators actually satisfy some kind of algebra, and that algebra is called the Lie algebra. Okay, so
Sir?
what I'm trying to do, I'm trying to give you the basically very hand-waving way to understanding this symmetry, such that you can directly use them in the quantum field and particles. Yeah, is there any question?
Yes, sir.
Okay.
So the question is that, as you mentioned, this generators,
Mhm.
so if I particularly talk about, let's say, SU2, the
Yes,
generators are so as you mentioned that it forms a orthogonal basis, right? So
they're independent. Yes, they're independent.
so I want to ask that independent means they follows this orthonormalization properties that they
Yeah,
should follow the orthonormal. So
yeah.
I want to ask that is it intrinsic? I mean, So the way the definition of generators we have made,
Hmm.
so is it very intrinsic that once the generators are defined in such a way, it has to follow the orthonormality?
Yes, yes. And that's the definition of independence, right? If the two matrices are independent, but the generators, we can write down matrix form. That's the matrix representations. So what you can check when you write down the matrices, okay, you can find out that you can take trace of product of two independent matrices and then calculate that what they should be.
Sorry, I could not understand. Can you please repeat that part, trace?
So the thing is basically, when you take out the vector space, you take an inner product, okay, of those states to be 0, and that you call them to be independent, right?
Yes, sir.
So similarly, when we talk about the generators, okay, then we'll see how we can define the inner product for them.
Okay.
Okay, yeah. Any other question? Okay. So now, the Lie algebra, without going into detail, what it tells you that if your Li are the generators, then Li Lj commutator is I F I J K Lj. Okay. So for any SUN, I runs from 1 to n square minus 1. Okay. So these Li are basically my generators. Now you see this commutator bracket, when you take two such generators, okay, then if I calculate the commutator bracket among them, then I do not create any other generator. I create another generator which belongs to that symmetry space. So that's how this algebra is basically closed. Okay. So second point is, by the way, this I is here index and this I is the complex number. That one has to be careful. Now in the left-hand side, what is that? Li Lj minus Lj Li equal to I Fij k Lk. Now you see that because commutator is by construction is antisymmetric. Okay, so that's why this Fijk is antisymmetric in this Ij index. Okay, but one can certainly prove that Fijk is completely antisymmetric in all its indices. So that means you change position of any two such indices, okay, you will get a minus sign. So F1, 2, 3 equal to F2, 1, 3, and so on. This F has a very special name. This is called the structure constant. Okay, because this actually give the essence of the symmetry group, and this F. Now, this particular commutator algebra is very similar whether you are working with SU2, SU3, SU4, whatever. What will be the difference? There are two certain differences are there. One is the number of generators are different. So for SU2, I runs from 1 to 3. For SU3, I runs from 1 to 8. Another thing, the structure constants are basically different. Okay. So SU2 structure constants are different than the SU3 structure constant. Now, if I go back to the SU2 case, then I will see that Li is nothing but my sigma by 2, where these are my Pauli matrices. Okay. So my L1 is half 0, 1, 0. L2 is half 0 minus I 0. And L3 is half 1, 0, 0 minus 1. The reason of this half is that of the normalizations. If I take trace of Li square, that should be half delta, or this is the maybe more Li Lj is delta Ij. So this is the orthonormality condition that will use. Okay. This is when Li's are in the fundamental representation. Yes. Okay. So that you can immediately process. That's why when I'm writing this algebra, we have to remember that this algebra is written in terms of normalized generators. Okay. So if I change the normalization of the generator or multiply by any random number, they won't satisfy this algebra. That's why Pauli spin matrices, that's a common mistake many people do. You have to be careful that Pauli spin matrices do not directly satisfy the algebra. Rather, the normalized Pauli spin matrices, what sometimes you call them tau I. Okay. And this is how we normalize our generator. That you take any tool generator, you take a product and take a trace, it will be 0. Okay, that's how they are independent. I mean, that's how we define their inner product actually. So now this is the algebra and generators and their algebra. But what about the representations? So SU2 also interestingly gives you very similar to the notion of angular momentum. Okay. Now let me go back to the angular momentum and then connect the SU2. I think that would be useful and for you. So if I start with the angular momentum state J, then for a given J, how many projections of Mj I can write down? That is minus J to plus J with unit interval. Right? Now, if I do that, that means my Mj for any value of J, it is always 2J plus 1. Right? Now, because of 2J plus 1, so that means if I start with the J, then I can have these many states, J, J minus 1, and then I'll carry to J minus J. So this is basically 2J plus 1 number of states. Now, what are the possible value of J can be? The possible value of J is basically, it cannot be, the lower value of J is basically half. It cannot be 1/3 or 1/4 or something like that. Why? Because it fits, J is determined basically the eigenvalue of the L3. So you see why the normalizations are important now. So you have the eigenvalues plus up and minus up because it has a J equal to half, spin half, okay? And this has a two projections plus up and minus up. That's how the L3 or the sigma Z, what you call, are basically an important generator. Now, because J is half integer, or integer, of course, but if I even, so it's an integer, then 2J plus 1 is integer. Even when J is half integer, 2J plus 1 is always integer. Okay. So then what is the value? What is the meaning of this integer value? 2J plus 1. This 2J plus 1 is a number which tells you that for a given value of J, how many states I can create. So I can create a multiplet, okay, which is 2j plus 1 dimensional, and that I write down in this particular form. So I can collect all those states which shares a similar quantum number. So if these states, all these states have a similar value of j, so that's why I can collect them, and then I found that for a given j, I have 2j plus 1 number of state. Okay. So now you see the minimum value of j equal to half. So my 2j plus 1 is basically 2, and this is the lowest dimensional representations of SU2. Okay, this is the first non-trivial representations of SU2. Who is it? And this is also called the fundamental representations. Now, depending on the dimension of the representations, when you write down the generators in the matrix form, the order of the matrix would be the same. That's why when I'm writing the generators in this particular form, I call them the generators in the fundamental representations, right? And that's what it's supposed to be, because otherwise they cannot just act on them. Now about the generators, again, to understand the transformation property. So what we have L1, we have L2, and we have L3. So each are independent generators, and they will generate independent rotations. So if they generate independent rotations, that means I need to assign an independent rotation parameter with them. So I just associate some θ1 with them. With the L2, I'll associate θ2. With the L3, I'll associate θ3. So now for the U1 case, it is like e to the power I density times theta. This is how the transformation was done. So I'll mimic this very similar idea, and then for the SU2, the transformation will be e to the power I L dot theta, which is equivalent to the power I Lj theta j, and for all j equal to 1, 2, 3. So this is how the SU2 transformations are done. Now see, this is basically acting on the state. So if I start with the SU2 representations, which is psi, now what I have to fix first, I have to fix the dimensionality of the representations. Dimensionality of the representations. Okay. And for example, if I set my dimensionality of the representation, which I call D, equal to 2, that means psi has two components, psi1 and psi2. Okay. And then if you ask how this psi transform under this SU2 symmetry, so that would be psi transform as psi prime equal to the power I L theta psi1 psi2. Right? Now you see L, if it has to act on this 2 by 1 column matrix, L is basically a 2 by 2 matrix. And that's what is consistent now. That is the fundamental representations or two-dimensional representations. So generators are also in the two-dimensional rotations like this. Now if my D equal to 3, then my psi will be psi1, psi2, psi3. So I'll have 3 elements will create that state. Then my transformation property will be psi prime as e to the power I L dot theta acting on psi1, psi2, psi3. Now, what is the important thing that you have to be careful here? I am changing the dimensionality of the representations, but I am not changing the symmetry group. As long as I am not changing the symmetry group, the dimensionality of the group space. So this is very confusing sometimes. The two things. One is dimension of group space. Okay, and another is dimension of representation. So for a given group, the dimension of the group space is basically fixed. Within the same group, I can have different kind of representations. That's why I can create different representation dimension. And in the case of SU2, how you can understand this? For example, when you talk about the addition of angular momentum, right? And then you start with two spin half state, and then you create spin one state, spin two states, spin 1.5, and so on, higher spin state. Now, these dimensions of the representations, which I call capital D, so this capital D is basically 2j plus 1. Now, when j equal to half, my d equal to 2. When j equal to 1, d equal to 3. J equal to 3 by 2, d equal to 4, and so on. But all the angular momentum, when you talk about, your number of generators are fixed because the dimension of the group space is basically fixed. Okay, so when you look into this inner structure, this will look like Lj theta j, but still your j runs from 1 to 3. But now these Ljs are basically 3 by 3 matrix. So number of generators are same, but what will be the representation, what is the actual form of the generators, that will depend on what is the representations that you are working with. Okay, yeah, up to this part, any question? Okay, so we don't need to look for very large representations of SU2 for the case of standard model. We only require basically SU2 fundamental representations, which is two-dimensional, and the adjoint representations. Okay. So adjoint representation for SU2 is equivalent to finding a spin one representations.
Sir,
Yes.
can you please explain again what is the dimension of group space?
Okay. What I'm saying, there are concept of dimension. I have twofold. One is dimensionality of the group space, which is, that means basically how to calculate the dimension of a vector space. You calculate the number of independent basis vectors, right? So here the generators are basically forming the basis in the group space. So dimensionality of the group space is basically number of generators. And the number of generators are a very fundamental quantity for a given symmetry. So that's why for a given symmetry, the dimension of the group space is basically fixed. But now, within the same group space, I can perform the tensor product. Okay? When we perform this tensor product, then I can create larger and larger representations. It's very equivalently what you do basically in the context of angular momentum. You start with angular momentum equal to half, but what you do, you just add those angular momentums and create 1, 1.5, 2, 2.5, and so on, higher angular momentum states. But still, your symmetry space is SU2. That means addition of angular momentum is equivalently a method of calculating higher dimensional representations of SU2 without altering the symmetry. Okay.
Okay, sir. Yes, thank you.
Okay. Okay. Any other question? Yeah, please don't hesitate to ask the question. Huh? Okay, so that was the fundamental representation we talk about. So now what is the adjoint representation? In case of SU2, you can think of it's a spin one representations. Okay, and this adjoint representations is by construction is real representations. Okay, that means if you take a representations and you take a conjugate of that representations, okay, it will be real. We'll see when it is not real, because SU2 has a pseudo real representation, so we'll not go into those directions, but this is a piece of information there. Now, when you write down the SU2 algebra specifically, then your Fijk is nothing but the Levi-Civita. Okay, so this is the Levi-Civita tensor, okay, and this is the structure constant. Now, why the structure constant is important? Because to construct generators in adjoint representations. And how do you write down the generators? So if the generators and the adjoint representation, write down the T, so you take ith generator Ti, and if you write down its matrix form, then you write down the jkth element of the ith generator is nothing but the minus I epsilon ijk. So this is how you construct the adjoint generators using the structure constants. Okay. Now you see one of the important thing, as I told in a previous discussion, that when the dimension is 3, that means this representation is in the adjoint representations, right? And then I need these generators to be in a 3 by 3 matrix form. Now, if I construct this way, what is the value of j and k? Each I, j, k runs from 1 to 3. That's why this becomes, by construction, a 3 by 3 matrix. Right? So now I will generate 3 matrices. Look, number of matrices are fixed, but instead of there being a 2 by 2 matrix, now they become a 3 by 3 matrix. So this is the way we will construct our SU2 generators, SU2 3 generators in a 3-dimensional or adjoint representations. And because the representation dimension is 3, that's why each generator will be a 3 by 3 matrix. And these generators will act on this state in this following form. Okay? Okay. So this is how
Sir,
this is.
what does
Yes.
sir, what does real representation mean? Is it mean all the generators is real, or
All the
generators is real element of generator? Means if it is a matrix,
okay,
all the elements.
okay, the representations are real. The generators, we don't comment on that thing, okay, because generators are always Hermitian for the SU2, right? So irrespective of which representation you are working on, that all the SUN generators are Hermitian. The representations are real in a sense, because if you take any representations and you take a conjugate of that, okay, that remains same. That's why they are called the real representations. Okay. The conjugation will not change the representations. And what kind of conjugation? When you talk about the CP, T, all those things, it will be more clear.
Okay.
Yeah. Any other question? Okay. So now we'll ask the question how to construct higher dimensional representations. Okay. Yeah. So there is an interesting technique that we'll talk about. It's called the Young diagram technique. So I'm not going to be detail about them. So I'll just briefly mention how to do that. So Young diagram technique, basically, it's a very generic technique of the addition of angular momentum. But as you know, the angular momentum addition you can perform for SU2 only. That certainly you cannot use for SU3 or other SUN. But this Young tableau actually give you a handle to construct the higher dimensional representations for other SU groups, for example, SU3 and so on, which will require to understand the Standing model. Now, how to calculate this thing? So, if I take a fundamental representations, so let's talk about the SUN fundamental representations. So the dimension of the fundamental representations, maybe precisely if I say lowest one, because you can have a multiple fundamental representation. So the lowest dimensional fundamental representations, their D is equal to N. For example, if I have a SU2, the dimension will be 2. If I work with SU3, the lowest dimensional fundamental representation will be 3. For SU4, that will be 4, and so on. Okay. So then that is represented by a single box like this. Okay. Then there is something called the anti-fundamental representations, again corresponding to lowest one. So which dimension we call as a n bar. So bar represents the conjugate representations. Okay. Now when I was saying real, for those representations for which n equal to n bar, we call them real representations. Okay. So this is depicted by n minus 1 number of vertical boxes. Okay. This has the n number of vertical boxes. And also we use the notion of symmetric boxes along the row. That means if I have these boxes aligned in a single row, these are all symmetric boxes. And I'll also encounter something called the anti-symmetric boxes along the column. Okay, that means if I have boxes like this, these are anti-symmetric boxes. Okay. So now,
Sir, in which sense they are symmetric or antisymmetric?
I cannot hear your voice. Can you be a little bit clear?
In which sense they are symmetric or antisymmetric? Boxes are.
Okay. So what we can, it will be clear actually. So when I talk about some fundamental representations, for example, let's say n, okay. So these are associated with some kind of vector, with some index ii. Okay. And then when I construct these boxes, for example, this I write down as psi ijk. So if I calculate through this tensor product, a new tensor with rank 3 ijk. Now, if this is a symmetric tensor, that means a symmetric in this indices ijk, that will be represented by a diagram where you have boxes along the row. But if let's say, I have a representation which is represented as an outcome of some antisymmetric tensor, antisymmetric in the indices ijk, then all the boxes will be in a single column. and that each box represents any kind of index, and there, if you change them, it becomes minus sign. From that perspective, symmetric and anti-symmetric. Okay. Okay. Any other question? Okay. So now let's see how to construct basically for the SU2, because that's the simplest one. And not only the simplest one, we can verify that using our angular momentum algebra. So when I have a, let's say, J1 equal to half and J2 equal to half, so then in terms of the representation dimension, I call D1 equal to 2 and D2 equal to 2, right? Because D is basically 2J plus 1. So if I take two states having angular momentum half and half, is equivalently saying I'm playing with two states, each are two-dimensional. Okay. Now, what is the meaning of J1 plus J2 is half plus half vector, okay? And this gives me basically 1 plus 0. That means what I'm adding this angular momentum, in this language, I'm taking a tensor product of these two states, okay? And then I am creating these two new states, which has angular momentum 1, another is 0. Now, what is the dimensionality of the state corresponding to spin or angular momentum 1? 2J plus 1 if you use, then that becomes 3. And for 0, this becomes 1. So you can see immediately that I have created a new representations which is higher than 2. Here, what I was doing, I have created a new state of a spin 1 which is higher than spin half. So creating a higher spin state is equivalently in this language creating the higher dimensional representations. So this I can check immediately from the angular momentum. Now, how I can use the Young diagram technique such that I can, without looking into this part, I can independently calculate this one. So that's what we do. So now, what is the diagrammatic representations of your 2 and 2? As I told you, the fundamental representation is given a single box. For SU2, the fundamental represent two-dimensional. So this is equivalently, you have a one box times you have another box. Let me call them A and B. And then I have to set up some kind of thumb rule. Those rules are basically mathematically generated, but as I said, I will not go into detail about the origin of the rules and so on. Instead, I'll give you the rule. Let's write down here. First rule is that we cannot have any diagram, okay, where the number of boxes in the ith row, and if you have a number of boxes in the jth row, so this ni is always greater than equal to nj. That means this is the diagram that I have drawn, is a valid diagram, but if I have drawn this kind of diagram, right? So that is not allowed. Okay. Now,
Sir, can you please explain this again?
okay. What I'm saying, the first thumb rule while creating this box, taking the product and gluing them and creating a new diagram, we have to follow some thumb rule. One thumb rule is that we place the box in such a way, we glue them in such a way that the number of box in the above row is always greater than equal to the number of boxes in the lowest row. And all lowest rows. That means you cannot have this also, because then number of boxes in this row is less than number of boxes in this row, which is not allowed. So I cannot draw that diagram. Okay, this is the first one. Second, while drawing, we have to start filling from left. What does it mean? That if I have a box here and I have another box, I will fill this from here. Okay. In first, I fill like this way. But for example, let's say if I get a diagram in this particular form, this, okay, this is not allowed, because while creating the diagram, what you have done, you have placed this box here without placing here. So you have to start placing the box from left. If you saturate the space, then only you can go on the right. Okay, so that's why this is not allowed, but this is allowed. Again, if you have a diagram like this is also allowed, because you have start fill first, then you don't have any other box left, so you don't put anything, keep it vacant. So this is allowed. Okay. And number 3, avoid duplicates. That means if you have a 2 boxes, okay, you draw only one diagram like this. Okay, so you name it A and B. Okay, or you can make it A and B, but certainly you cannot make it like B and A, because this A and B are just for you are putting this tag to track them. So these are the duplications. So if these A and B are basically equivalent boxes, then I cannot write down these 2 boxes separate, 2 diagrams separately. I'll draw only one of them. Okay, so this I'll not draw if I drew this diagram already. And 4 is basically counting of dimensionality. That if you are given any number of any, let's say, something like this, okay, maybe, okay, yeah. So if I have, let's say, this kind of arbitrary diagram, which is consistent in a sense, look at number of boxes in the above row is always greater than number of boxes of the lower rows. And also I have filled up first the left and then I move to the right. So they are consistent. So I drew, so first using the tensor product, like diagrammatic this thing, I will draw the valid diagram. But your job is not done there. What you have to calculate then, you have to extract the dimensionality associated with this diagram. How you do that thing? You do the following way. For any given SUN, you start with this to be n, and then once you go in the right direction, you increase n by 1 unit. So this will be your n plus 1, this will be n plus 2, this will be n plus 3. And then when you come down vertically, you decrease by 1 unit. So this will be your n minus 1, n minus 2, and n minus 3. Okay? And then again, you start with n minus 1. So you increase by 1 unit. So it is n, and this is n plus 1. Okay? So that's how you basically number your boxes. Then your dimensionality D will be some numerator n versus some denominator function D. Now your numerator function, now your numerator is basically product of all these numbers that you have written. Okay, each boxes and n minus in. So for every row, you collect all the numbers and just a product of all the numbers. And if you calculate that, you get basically numerator. Now, how to calculate denominator? To calculate the denominator, we have to be careful. Yes, we draw that diagram again. We'll explain that thing. Yeah. And then to calculate the denominator, what you do is to start with the extreme right of the first row on the outside. And then you take straight horizontal line and you stop once there is no box left, like here. And then you come down straight and make an exit. And with this process, the horizontal and then vertical, there is no curve or something like that. In this process, you count how many boxes you have encountered. Okay. So then count 1, 2, 3, 4, 5, 6, 7. So you have 7. And then you start for the second row and you play the same game there and then stop and then make an exit. And then count how many boxes you have done. 1, 2, 3, 4, 5. So you make 5. But here also you can do third row, like here, you make 1, 2, and for this, you make 1, so you get 1. So for all the rows, you reach till the last box, and you make an exit vertically in the last column, and you get the number. So your D should collect basically this number. So this is basically collection of 2 into 7 into 5 into 1. Then you play the same game with next column. Like for this one, you come here and then make an exit here. So 1, 2, 3, 4. Okay, so you get 4. And then you make the similar kind of thing. You collect 4 and all those numbers. For second row, for second last column and last to last column, last to last column and the last column, you make all these numbers. And this collection when you get, that's what give you basically D. And then you calculate D equal to N by D, and this will be an integer. This has to be. And this will be the dimensionality of the representations corresponding to this Young diagram. That is how you compute the higher dimensional representations for any SUN group. Okay. Any question? Okay. So
Sir,
now
this process is same for hello, sir.
Yeah.
This process is same for all the group, or it is true
All
for
the
only
SUN, yes, this works for all SUN groups. Yes.
Okay. And when you counting the denominator part, is there any double counting when you going to the
No, if you
vertical
do in
line?
this way, there will be no double counting because all the trajectories are basically unique. Okay.
Oh, okay.
Okay. Okay. So now let's go back to this one now. So we have learned how to do that thing. So then we know with this we can draw only these two diagrams. So then how to calculate the dimensionality for this diagram? So we are working with SU2. So this number will be 2 And as I told you, if you go from the right hand side, we go by 1 unit, so this will be 3, right? So then what is my dimensionality? Numerator is a product of these two numbers, and if I calculate, I have only one row, so I just take an exit here and here. In the first exit, I get 2. In the second exit, I get 1. So this is 3. So I get 3 dimensionality here. And now for this is my 2, as I told you. And when you're coming downwards, you reduce by 1 unit, so you get 1. So your dimension will be 2 times 1 by, now here if you start, I take an exit. This is 2. Okay, this is 2, this is 1. But now the 2 rows are there, so I have to make another one. This is 1. So 2 times 1, and that is 1. So that's why I can write down now 2 cross 2 equal to 3 plus 1. So this we can generate now using the Young calculator. Okay. So this is the way we can create the representations of much more higher dimensions. Okay. Is there any question?
Sir,
Yes.
how have you written this? Like this box A cross box B is as the right hand side, because as much as so in the line above you have written 2 cross 2 is equals to 3 plus 1. So how these boxes are representing this 3 plus 1, can you please explain?
Yeah. So up to this part is okay.
No, the point where you mark, this is the problem actually. I mean, how do you write that from the arguments that you made? If you please explain.
Okay. So you start with 2 cross 2. In diagrammatic language, we are taking a tensor product of these two boxes and the rules that we have learned. That means I can glue this box B only below A or sidewise A. If I put on top, that will be duplication. So I'll not get. So I'll get basically A, B, A, B. That's the two independent diagram I can draw. Now, once I draw the diagram, I use the calculation of the dimensionality formula from here. I know I start with the n and so on. So when I am writing this, I have to calculate the dimensionality of this box because that's what 2 cross 2 implies. Okay. So in this way, because SU2, so this is basically 2, you go horizontally, basically 3. So that's how using this prescription, if I calculate the dimensionality corresponding to this box is 3. Similarly, I calculate the dimensionality corresponding to this vertical box, which is 1. And that's how I can write down 2 cross 2 equal to 3 for this box, 3 for this diagram, and 2 for this diagram. That's why this is 2 cross 2 equal to 3 plus 1.
Yes, sir. Thank you. It is okay.
Okay. Fine. Okay. So now, apart from this, calculating this 2 cross 2 with a 3, the presence of 1 is basically very important here. Why? Because what is the meaning of this 1? So this 1 is the singlet representations. And that is what is our Lagrangian is. Right? So in this language, our Lagrangian is singlet under rather each internal symmetries. Now, if I focus my internal symmetry to be SU2, right? So then, if I think about that, okay, phi is a two-dimensional SU2 two-dimensional representations, which is the complex two-dimensional representations. Okay, that means you can write down phi as a phi 1, phi 2. Okay, each are complex. This is also complex. So my phi dagger is phi 1 dagger, phi 2 dagger, and this is also, you should write down 2 bar, but this is pseudo-real representation, so SU2 2. Now, if you remember, in the case of U1, when you talk about the invariance, where it was, yeah, here, right? That phi dagger phi is an invariant quantity we have checked. So that is U1 invariant. But now the question is basically, are they SU2 invariant also? So then if I calculate phi dagger phi, what does it mean? It means basically I am calculating actually tensor power 2 cross 2. Now my goal would be to check through this tensor product, can I create at least one state which is singlet? Then only we can say that if I take SU2 two-dimensional representation, I can write down that as a part of the Lagrangian because I can create a singlet of SU2. So my Lagrangian that term will be singlet. So now 2 cross 2, we know this is 3 plus 1, but this presence of 1 here tells you that I can create a singlet out of this two-dimensional representation. So this implies that phi dagger phi is SU2 invariant. Okay. Now, if I have a phi dagger phi whole square, that means 2 cross 2 whole square. So what you can write down as a 2 cross 2 cross 2 cross 2. Now I can create singlet in multiple ways. For example, if I focus on this, I get 3 plus 1. If I focus on this, I get 3 plus 1. And if I take 1 from here and 1 from there, and they give me another 1, because 1 cross 1 is nothing, it's a 1. So that's why this is also SU2 invariant. So now you can say that if I have a phi, which is SU2 2, and under U1, let's say it has a charge plus Q. So the Lagrangian that I'm writing del mu phi dagger del mu phi minus m square phi dagger phi minus lambda, or in the previous language was C2 phi dagger whole square, that is invariant under SU2 was U1. That means it is invariant individually under SU2, it is invariant individually under U1. That means if my symmetry is SU2 cross U1, the whole Lagrangian is invariant under SU2 cross U1, both the symmetries. So if my symmetric group is SU2 cross U1, then this is a valid Lagrangian with the phi having these representations of the scalar field. That is how we can create our own Lagrangian to the representations theory and considering the invariance and so on. Okay.
Sir, you says that it can be, there has a possibility that it can be a singlet, but it could be a triplet also. So how can we ensure that?
No, it's not about the ensure. I will create both the states, triplet and singlet. But only the singlet part will be part of the Lagrangian. That's all.
So psi dagger psi is always a singlet.
Phi dagger phi, when you calculate it component wise, for example, when you add a spin 2 spin half state, you create a spin 1 state and spin 0 state. How do you calculate the spin 0 state? The antisymmetric combination of the spins, right?
Yes, yes.
Similarly, here also, when you take component of the phi's, okay, you calculate the
Yes,
antisymmetric part, and that will be your part of